Okay. Chapter 14, chemical equilibrium. So we started off by going through our K value, right? That is products over reactants raised to their stoichiometric coefficients. We talked about in chapter 13 where our rate law just has to do with the reactants. There was a K value there, it's lowercase k, it's a constant. And that doesn't necessarily have to be raised to that stoichiometric coefficient. Here, these ones, they are. And we're given, all right, so here we have our Kc, products over reactants, raised to those stoichiometric coefficients. Kp, how is that related? Set up the same way, we're doing partial pressures. So Kp only for gases. Our Kc, we're only going to include gases and aqueous in those K expressions. Everything else is for 15. All right, where does Q fall into this? Right, so as long as we know it's products over reactants, right? If we get a Q value that is greater than K, what does that mean? So K is for when we're at equilibrium. We're not at equilibrium, but we end up with a Q value that's greater than K. We have too many products, not enough reactants. So we need to go in reverse so that my products get smaller, my reactants gets bigger, and then that'll get me back to equilibrium. All right. So in this case, here, I'm going to shift backwards to get to equilibrium. If my Q is less than K, that means I have still too many reactants, and I got to turn some of my reactants into products. All right, so it's important that we can do this Q at any time and then compare it to our K value. Hess's law, I think we're pretty good at, right? Now, since when we do our calculations, it's products over reactants, now all that math is kicked up, right? If I reverse a reaction, what happens to my K value? Inverse, right? Where, remember, when we did our delta H, when we did our calculate delta H, it was products minus reactants. Now we're doing products divided by reactants. That's why that math level is kicked up a notch there. If we multiply an equation by 2, we square our K value. We introduced our ice boxes here. Make sure if one thing changes in our equation, they all have to change. Right? We can't just say some of our CO was turned into CO2. No, we have to. Everything changes. Right? That was one of the things where we would have like initial concentrations, and we would have one final concentration. You can't use those necessarily straight into your K value. Instead, you got to set up the icebox and see how everything must have changed to get there. And then once you have those finals, then we can plug those in. Chatelier's principle, we like that one. Concentration, we're good, right? If we just have our reactants going to products, right? So if I add some reactants, I have too many reactants, I got to go forward to get back to equilibrium. The K value doesn't change, right? But we're pushing us away from equilibrium, a Q value, to get back there. The other, I think the part where we gotta just remind ourselves that we could have like a side reaction occurring. Maybe we added something that's not necessarily in a reactant or a product, but it'll react with maybe one of our products. So if it's something that'll end up taking away our products, that means we don't have enough products, we get more of the forward reaction to occur. Pressure, what does that only affect? Gases, all right? And if let's say we have 2 moles of gas on this side, 4 moles of gas on this side. If I decrease the volume, the pressure increases. What do? How does my system get back to equilibrium? I go to the side with less moles of gas. That's going to relieve some of that pressure that's there by turning some of the side with more moles to fewer moles. Temperature. Temperature is the only thing that's going to change what? This will actually change our K value. All right. This will shift it. When temperature changes, what do we need to know about our equation? We need to know our delta H value to see if it's endo or exothermic. An increase in temp favors the endothermic reaction. So if this was endothermic, it would shift us in the forward reaction. What does the catalyst do with equilibrium? Nothing, just gets us there faster. All right, it's still going to be the same equilibrium. It's still going to be the same K value. It's just going to take less time. That's more the kinetic side of it. All right, but we're still going to end up with the same amount of our reactants and products. Temperature. Oh.
Like which K value?
KP. P for pressure. The KC. Right. KP, KC, molar concentrations, KP, gas pressures.
Which one, like, you don't include the aqueous?
None of them do you include liquid or solids. And we're not going to have a mixed equilibria where we have like aqueous and gas or something like that. You have one or the other. So.
Can you go over KSP, or is that like later on?
That is later on.
Okay.
Don't you worry, we're going to go over it. That's 16. All right, 15. Now we're getting into our acids and bases. All right, this is still the basics of it. All right, chapter 4. That was when we were introduced to acids and bases. There was just like kind of like strong acids, strong bases, equivalence point, moles equal moles. Now we're getting into Bronsted-Lowry acids and bases. An acid is going to donate an H plus to produce a minus. This is the exact same equation. Right? Yes, same equation. We might do this one in case, like they said, identify conjugate acid-base pairs, something like that, right? Here we can see HA is acting as the acid because it's donating the H, forming A minus. So there's our acid, there's its conjugate base. And then water must be acting as a base because it's accepting one to form H positives. Right. A base in water, we can have A minus. We can have A minus plus H2O. We got HA and OH minus. So here we would have a Ka value. Here we have a Kb value, right? How do we know this is acting as a base? It's accepting the H positive. Right? All right. I think we're pretty good with like our Kw, pH, pOH, doing our calculations there. Again, we get those equations down here. All right. We get our Kw. We get our pH plus pOH is 14. We have what Kb looks like. We have what Ka looks like. Where's it? Ka1. All right. Oh, there you go. We have our Ka. We have our pKa, pKb, that kind of stuff. And we have our Henderson-Hasselbalch. What else we got? Strength of acids. Right. These are all weak acids, or the ones we're talking about, weak acids. So our K values are going to be really small. Right. Within those, if we have a larger Ka value, that means it's a stronger acid. Why are our acids considered weak acids? What's going on at that molecular level? Strong attraction to each other. We'll say even like strong bonds to each other. So that HA, that bond there, that's really strong. They want to stay together. They'll float around in the water, but they won't separate very much. And that's why we have the Ka values that are so small. The relationship Ka to Kb, all right. Percent ionization, that's just the amount that it would ionize, right? That's like that would be like our H plus over our HA. It's the same calculation we do when we make our assumption, when we do our icebox. If we have to do, 0.2 minus X is about 0.2. Conjugate acid-base pairs, right? If HA is the acid, A minus is the base. This chapter 15, that was like Ka or Kb, right? Where there wasn't a whole much to it. Chapter 16, that's when we start to mix things. It gets a little bit more confusing. Good on 15? All right. It's still 15. Sorry. Diprotic, polyprotic. What do those mean?
How many H pluses?
Yeah, we could just have multiple H pluses. We could have something like H3, PO4, right, where there's 3 H's ready to be ionized. Right. Molecular structure and strength of acids. That kind of gets in here with these. I wouldn't spend too much time on this. This is the idea. Like we might have HClO, HClO2, HClO3. Here, which one of these would be the acid with the highest Ka, the strongest acid? This is where we look at, here these are oxoacids. We would look at our oxidation numbers of that central atom. And the higher the oxidation number of the central atom, the stronger the acid is going to be. The lower the oxidation number is, the weaker the acid is going to be. Just makes that bond more polarizable. Meaning, so that H isn't bonded to the Cl, it's bonded to one of the O's, and it just makes that more polar, and it's able to get ionized.
So H and O are always like the same, right? H is always plus 1, O is always
Yeah, for acids and bases they are. Yeah. Right. So that's one way to do it. The other way to look at would be something like this. All right. Here, now instead of changing the oxidation number of the central atom, now I'm changing the central atom. What do I care about here? Whatever central atom has the highest electronegativity, that's going to make for a stronger acid. So here, HClO3 would be stronger than these ones because chlorine is more electronegative than bromine or iodine.
Meaning that it would like pulling everything closer to the harmony of the system.
So you end up with like the Cl like this, and it ends up pulling the electrons in tighter overall and making this bond more polarized. And now, since that's more polarized, it's easier for the H plus to ionize away. I doubt there's going to be much stuff on there. Maybe a question or two on the multiple choice, something like that. Not a ton on there. Acid-base properties of salts and oxides. We really struggled with this. We still struggle with this. That is that idea, right? If I put NaF into water, what's going to happen? First off, it's going to dissolve. Why is it going to dissolve? Why is it going to be soluble? Na is a group 1. All right, now what can happen? What can this F minus do in the solution? Can it donate an H plus? No, that doesn't make any sense, right? But what can it do? It can accept an H plus. Right? It can accept an H plus. We know HF is a weak acid, so there's strong attraction between the H plus and the F minus. Since that strong attraction, some of those F's can take an H away, and we end up with our hydroxide there being produced. Right? HF has a Ka value. That F minus, its Kb value. That's the one that Ka times Kb is Kw. Right? HF acting as an acid, F minus acting as a base. So that's that whole conjugate acid of a weak base, conjugate base of a weak acid having acidic basic properties. If it came from something strong like HCl, it's not going to have any effect on it. The opposite of these ones would be something like NH4Cl. The Cl, spectator ion, goes away. What can this NH4 plus do? Right. It can donate that H plus, acting as a weak acid. NH3 is a weak base that has a Kb value. This one has a Ka value that's related with the 1 times 10 to the negative 14. All right, that was 15. 16. All right. Now we got into, instead of just having like a Ka problem or a Kb problem, we kind of have both going out at the same time. So our common ion effect, HH, Henderson, Hasselbalch, and buffers. The idea here is we start with a weak acid. Say we have HA. And we add to it some A minus. So now there's both weak acid floating around and its conjugate base floating around. All right. Now if I add an acid to this, say HCl, a strong acid, I have weak acid and its conjugate base floating around in water. I can neutralize that acid. What part of this is going to neutralize that acid? The A minus, right? H plus A minus yield HA. So all that happened was some of my A minus turned into HA. If I added a base to this, all that happens is some of my HA turns to A minus. So thinking about Henderson Hasselbalch, here, when we did our calculations with this, the pH was really close to whatever the pKa was. This log of that didn't change my overall pH very much. And that's why as I add these, an acid or a base, to the buffer system, my pH doesn't change very much. I think about my titration curve, right? I'm somewhere down here right now. My pH isn't changing very much. Why? It has the ability to neutralize whatever we add to it. Right? In this case, I have HA. I'm adding the OH. And this reaction is occurring, and I'm just changing the amount of HA compared to A minus. It's not until I run out of HA, or get close to running out of HA, that my pH can change drastically. All right. So buffers, weak acid and its conjugate base, weak base and its conjugate acid. If I have something strong, it doesn't really do much for me. Right? It's not going to have that ability, because you need that strong attraction between the H and the A. What else we got? For our titrations, all right. All right, our titrations here. Right here. This is a Ka problem. We have pretty much all HA here. At the equivalence point, now I have A minus. All my HA has been converted to A minus. And it's a Kb problem. This is the one where, right, we would have two ice boxes, one ice box just to figure out how much A minus I have, and then one for the reverse reaction that occurred. HA plus OH, right, yielding the A minus and H2O, and then it's that reverse reaction. All right. In here, I have both HA and A minus. So what equation can I use? I can use my HH to get the pH. Right? All that's changing is that ratio of A minus to HA. It actually just turns into like a excess hydroxide problem. Once we get past that, now it starts to go up so much because you're just adding excess base. All the bases in the form of the A minus is there, but you're putting in a strong base now. It just turns into, if you put an extra 3 milliliters in, okay, just go like moles and figure out how much OH you have still floating around All right. As you keep it, you're starting to use up all this. They call that the buffer capacity, right? If you have a lot of high concentration of HA and A minus, it has a big buffer capacity. It's not going to change for a long time. If you have low concentrations, there's not a lot of them, you're going to get through that equivalence point faster. What's the special point or the useful point that we can use here? Here's our equivalence point, right? It's a pH. It's a pH and a volume. If this was a weak acid in a strong base, where would my pH be? If this was a weak acid in a strong base at the equivalence point. pH greater than 7 at the equivalence point, right? Because some of my A minus is going to react with water to form HA and hydroxides. Since I form some hydroxides, a KB problem, I end up in the basic range. Strong acid, strong base, pH equal to 7. pH less than 7. How about the weak acid, weak base? Usually, hopefully nothing. Hopefully we don't get asked. But we could compare the Ka to Kb. The Ka of the weak acid, the Kb of the weak base. If Ka is greater, that means we're going to have more acid there. It's going to be slightly more acidic. Kb greater will be slightly basic. All right, how about getting back to this graph? What else can I get from here? Half equivalence point, right? If this was 20 milliliters at 10 milliliters, I can come up, come across, and that's going to be my pKa value, right, at the half equivalence point. At the half equivalence point, my HA equals A minus, because half of my HA has been converted into A minus. As I'm adding hydroxide, right, the hydroxide plus the water, or plus the HA, I'm getting the water in A minus. So as I'm adding the hydroxide, my HA is coming down, my A minus is coming up. When they're equal, at the half equivalence point, my pH equals pKa. Remember over here, this is the equivalence point. So that means my moles of HA equals the moles of OH added. Right? That means I've converted all my HA into A minus. All right, good. All right, indicators. Those are usually weak acids that just change color based on the pH. Right? They'll have a pKa value as well. And you want your equivalence point, right, to near the end point of our indicator. So that way it'll change color at the appropriate time, not too early, not too late. All right, KSP. Just as a regular old K, if we just treat it as a K problem, that might be more useful to us, right? We might have something like this, Va, F2. This is a solid, aqueous, aqueous, right? So if we just do a K expression for this, what would it look like? Va2 plus F minus squared, and that's it, right? That's KSP, right? It's not like a special, that's all of these are Ks, and it's just based on what equation we're using. We kind of specify a way for us to like kind of focus in on it. So here's our KSP expression. Solubility, that's usually measured in grams per liter. Molar solubility, moles per liter, which we know, which we would call what? Molarity. Right? Just like our Ka, Kb value, these have really, really small KSP values. Right? Only a small amount of it's going to actually ionize. Most of it's going to say we're going to consider it insoluble. Most of it's going to sink down to the bottom. Only a really small fraction of it's going to actually dissociate. pH and the solubility of salts. We struggle with this one as well. This is the one where we have something like, let's say I had this BA. If I had this equation here, all right. If I added a strong acid to this, if I added H pluses, this tends to be more soluble in an acidic solution. Why? What can these H pluses do? Those can react with F minus. I'll put a double arrow to form HF. We know HF is a weak acid, so by putting the acid in there, H pluses and F minuses will come together. What happens to my concentration of F minus as I add those H's to it? It decreases. So now Chatellier's principle, I'm going to get more of the BAF2 to dissolve. All right. So this will be more soluble in an acidic solution. Again, I don't expect a ton based on that. All right. Complex ions. Would be something like maybe we have copper plus ammonium, and we're going to end up with a complex ion, meaning it doesn't form a precipitate, but we get something like this where everything's aqueous, and we'll have a K value for it. Usually, whatever the charge is, we have 2 times as many of our things here. It could be water molecules, like, right, we've seen water where we hydrate it. It could be ions. But again, just treat it as a K problem. The concentration of this over the concentration of those. That was 16 questions.
So for the complex ions, like how was it asked out on the test? And now, like I know you would just treat it as a K problem, but like what kind of problem would it, like even a complex ion?
They might talk about concentration. They might talk about like what's the, if this is the concentration of copper, what's the minimum concentration of the ammonia to get the complex ion to form, or something like that. You can always icebox it and go from there.
How can you like use what you talked about with the pH and solubility of salts? Like it'll just say like a strong acid like HCl was added, like
Yeah. They probably won't even say strong acid. They'll probably just say HCl is added. How will this affect the solubility? Or it'll be BAF2, and they'll say, how can you dissolve more BAF2? You could add more water. You could heat it up. You could add an acid to help dissolve it, something like that.